So my talk is, you can view it as a continuation of what Ciprian talked about, with a focus on different other aspects and other problems. It's still work with Ciprian. So here's what I want to focus about. So our goal is to explore expansive trajectories in auxetic deployable structures inspired by tilings. That would be the kind of thing that will be the thread through my talk. And why is that? Number one is that we may have seen parametrizations that actually give auxetic trajectories in such frameworks that have many degrees of freedom. The problem is not easy to find them. It would be wonderful, but it's not always easy. And although expansive motions are more restrictive in the sense they impose more conditions than auxetic ones, they are easier to detect and compute because they have a combinatorial characterization. So let's see how useful they can be. So here's an overview of what I want to talk about. I want to make a brief introduction to periodic expansive motions and maybe connect them a little bit with the finite ones. And then I'm showing you how to compute an expansive trajectory in a 4 degree of freedom tiling to deployment framework, one that was already on Ciprian's slides. And at the end, here are 2 take-home messages that you can look for them during the talk. So one message is that sometimes purely expansive motions do not suffice. So we have to use motions that are not purely expansive. So we can go only that far with expansive motions if we want to design a trajectory that is auxetic. And in particular, in this case, we'll see that auxetic behavior can be present. So a framework can still have auxetic motions even after the expansive part of the trajectory has been completed. So these are the take-home messages, and there will be others along the way. So I'm going to focus on a variation of this framework. So it's a periodic, non-crossing bar and join framework. It arises from a periodic tiling of the plane, and it has 4 degrees of freedom. So this is just a picture. You'll see animations shortly. And this one is not very symmetric. So here I have two classes of triangles, the red and the blue, by periodicity, I mean 2 orbits. And an interesting aspect of this is besides the 2 rigid triangles, there is only one face up to periodicity. So there is this star in the middle. And this framework in the position in which it is placed, it is what is called a pointed one. So pointed meaning that at every vertex, can you see my mouse? I'm just wanting to make sure. Can people see my mouse? Yes. Good. Yes. So at every vertex, there is an angle larger than pi. And this is an indication that the framework will have at least one auxetic, at least one expansive motion. And we want to take advantage of that. So in this large space of large 4-dimensional space of possibilities at every moment in time, you have a 4-dimensional infinitesimal space of motions, and over all the configuration space is 4-dimensional. There exist auxetic motions, there exist expansive motions. We'd like to design the trajectory in a way that will not require an explicit parametrization, because sometimes it's hard to find it, and we want to find it in an efficient way using expansive motions. So as you saw in Ciprian's talk, so this example is part of a collection of tiling examples. Of course, tiling in the case when everything is regular. So this comes from a paper of Grünbaum and Shepard from '77, tilings with regular polygons, except that we made nice frameworks out of them. So think of them as being as regular as possible. But we can also deform them and study their properties. But the 4 types of tilings, periodic tilings, they have different kinematic parameters. So let's quickly go over that. And again, I know Ciprian went over some of these properties. So this one has only 1 degree of freedom. So it means that you can only deform it along a single trajectory. And this can be immediately seen. You don't need to make any calculation. You can immediately see that because all faces are pseudo-triangles. So what I mean is you see that all of them are pointed at every vertex in all of these tilings. There is an angle larger than pi. So all of them are pointed, they have expansive motions, but this one is just 1 degree of freedom motion. And this is due to the fact that all faces are pseudo-triangles. So some are triangles. And here you can see the other type of face, a pseudo-triangle. A pseudo-triangle is a polygon as non-convex as possible. So it has only 3 vertices that are smaller than pi. Everything else is larger than pi. And you see this pattern in all of these pictures. There are pseudo-triangular faces here and here. This is not a pseudo-triangle, but it is still pointed. So we have pseudo-triangles here, pseudo-triangles here. This is not a pseudo-triangle, but when it is a pseudo-triangle, then it is 1 degree of freedom and expansive. The next one, well, this is tricky a little bit. So this one has 4 degrees of freedom because I have not braced the faces. If you brace the faces and you have these extra bars here, this actually would be a different beast, but without bracing the face, it has 4 degrees of freedom. So because the faces are convex, there are no expansive motions other than those that would keep the faces convex. And the only way to move it would be along a unique 1 degree of freedom trajectory that, what I mean, the only way you can move it, keeping the faces rigid, would be this unique 1 degree of freedom expansive motions. But if you allow deformations of the faces, then you'll have more degrees of freedom. The next one, this is also interesting. So this one has only 1 non-convex face. So this beast here in the middle is repeated periodically. And there are 2 ways of dividing it into pseudo-triangles. And again, if I view the squares as being fixed, it's one perspective. If I view them as deformable, is another perspective. So if I don't fix the squares, it has 3 degrees of freedom, but 1 degree of freedom, which would be wasted, so to say, by deforming the triangles, would not be an expansive motion. So there is a 2-dimensional space of infinitesimal expansive motions because of the 2 ways in which I can triangulate the faces. And I'll go a little bit in the background theory in a moment. I just want to give you a preview of what we can do with this theory. And the last one is the one that Ciprian also talked about. This one has 4 degrees of freedom, has only 1 convex face, non-convex face, right? And this can be divided in 14 ways into pseudo-triangles. So it's a lot of, there are a lot of ways in which infinitesimally I can move expansively. Not only that, but the space of infinitesimal motions form a 4-dimensional cone, polyhedral cone. And what I'm showing here is a 3-dimensional section of that 4-dimensional cone. And you see that this polyhedron is quite symmetric if the structure is symmetric, and it has 14 vertices, and each of these vertices refers to one way of subdividing the non-convex face into pseudo-triangles to get an infinitesimal motion that is expansive. And you can continue along that trajectory. So this is just a preview. I'm going now to go into more details on a particular example. Yeah, so let me start with a brief introduction of periodic expansive motions. Yeah, so first, infinitesimal ones. What it means is that as your framework moves, infinitesimally, all pairwise distances tend to increase, or stay the same. So none of them will decrease, so but all of them. Yeah, so there is not that some may not. Whereas in an auxetic deformation, this is not a constraint. So expansive motions are more constrained than auxetic ones. So now when I talk about an expansive motion, I mean an actual trajectory. So it's a finite trajectory, yeah, where at each moment in time, possible at the end, right, when you reach the end, the infinitesimal motion is expansive. So that is a trajectory, okay? So finite motion. So here's an example. So this is one of these structures, and infinitesimally, I can make a little deformation and more and more and more. So this together put next to each other continuously gives us an expansive motion, an expansive trajectory. So now expansive implies auxetic, but the reverse is not true. It's auxetic, it's a more encompassing definition. And this study was initiated a couple of years ago with in a paper with Ciprian, and now we are investigating a lot of consequences, and we came up across a lot of interesting problems, and that's what we are trying to share today with you. So Ciprian made the motivation already with respect to the motivation from material science. So let me dive directly into some mathematical aspects of it. Now, as I said, infinitesimal expansive motions, actually infinitesimal ones, form a polyhedral cone. So at every point in your expansive motion, there is an infinitesimal motion, yeah, an infinitesimal one, and all the possibilities in which you can move form this polyhedral cone. And this polyhedral cone sits inside the positive semi-definite cone of infinitesimal auxetic motions. Sometimes it coincides with it, sometimes sits strictly inside, sometimes the auxetic, the cone of the semi-definite cone of infinitesimal auxetic motions doesn't have expansive motions inside. Yeah, so this is an example for the framework that I was showing you previously. Now, there is something interesting, right? So in, as I said, it is a four-dimensional cone in fact, because we live in a four-dimensional space for this framework, but this is a 3D section, and the extremal race in the 4D cone becomes the vertices of this expansive motion polyhedron. So now the beauty of this is that expansiveness is essentially captured by pointed, in this case, we are talking about periodic structures, periodic pointed pseudo-triangulation. So it has a combinatorial characterization. And when you see a combinatorial characterization, immediately you think, okay, so how can I use it? Because usually combinatorics is easier to imagine and gives a structural understanding in this humongous world of possible trajectories in a four-dimensional space. So can we use it? So a brief description of what periodic pointed pseudo-triangulation is. I'm repeating this. So this is a little piece of one. As I said, it is a structure where at every point there is an angle larger than pi, and where each face of the tiling has exactly three vertices that are smaller than pi. And this one is maximal with this property. So if you try to put any other bar, add another bar somewhere, you are going to violate either crossing, if I were to put this one, or pointedness, if I were to put this edge. So then if I put this edge, there will be angles, there will be no angle larger than pi at this vertex. So it's maximal. So it's easy to construct essentially randomly. And so planar, pointed, and maximal. So this is the underlying theorem, is that periodic pointed pseudo-triangulations are, and that's it, flexible, and they are always flexible, always with 1 degree of freedom. And they are, the motion in one direction is expansive, in the other is contractive. And their unique infinitesimal motions are in one-to-one correspondence with the extremal race of the expansive cone. And any other infinitesimal expansive motion is a convex combination of those induced by the periodic pseudo-triangulation. So it's a convex combination inside the polyhedral cone. So it's plenty, four-dimensional one. Good, so consequences. Now, if I'm only focusing on pointed, not necessarily pseudo-triangulations, they are flexible, but with perhaps more than 1 degree of freedom, but they can be refined to pointed pseudo-triangulation. So in other words, if they can be refined, there will always be expansive motions possible. And they're generic. That's another very interesting property. So the degrees of freedom can be computed with the extension to periodicity of the Maxwell counts. So these are counts that actually come from work that Ciprian and I did. We proved that generically this is the case. So just looking at the quotient graph of the periodic framework. So the pseudo-triangulations are always generic. And the space of the infinitesimal motion is this polyhedral cone. So this is just a summary of properties. Okay, so now here's a question. So now back to forget this introduction. So now we have these nice tilings, and the people are interested in a lot in these auxetic designs that come from these very elegant tilings. And we may wonder, how wide can we deploy them? Yes, how they seem to be pretty packed. So how wide can we deploy them, and how can we get there? Yeah, so I'm going to talk about this. I'm going to talk about computing an expansive trajectory in a 4 degree of freedom tiling to deployment framework. So that's what I want to do next. Okay, I went pretty fast until now. Any questions so far? Okay, if not, let me continue. So this is the tiling, and this is another representation of it with a little bit of extra information, namely. So again, it appeared in Ciprian's. So these are the two orbits of triangles, and you can distinguish them both by the color and by the orientation. And what I have depicted here are the degrees of freedom as a chosen parametrization that we could figure it out. So first, you can rotate this. These dotted bars are the drivers of the motion. So you can individually move each one, individually and independently. They are independent variables. And finally, with this extra gadget, you can rotate one of the, let's say the blue triangle relative to the red triangle, and then you get another parameter. Yeah. So let me share one of these and show you how it behaves. Okay. So here I have on this screen, actually, I have two animations for two of the tilings in Shepherd, in Grünbaum and Shepherd, but let me start with this one. So this is the triangular one. So independently, I can deform, oops, this one. Yeah, I can deform the structure. And in fact, I can deform it and bring it to an almost spec configuration. And now if I change the orientation, actually, this is the tightest configuration that I can reach. Yeah, so we call this the tiling. And what we want to do is to get to a deployed version. So the deployed version, well, what I'm doing right now, it's a trial and error thing. Okay. Okay, so trial and error and thinking about, well, what could be the largest one? And with a little bit of playing around, I can say, yeah, this seems to be the top, the highest symmetry. Symmetry is an artifact. It's the highest area that I can reach with this kind of deployment, maybe a little bit of playing around to make it perfect. Okay. So this one has 4 degrees of freedom, and we found a parametrization, a very nice parametrization, and Ciprian told you about. But I want to contrast it with another one. So this is another deployment. I think we gave a talk about this maybe 2 summers ago or something. So this is one of the other tilings. This one has 3 degrees of freedom. And these degrees of freedom are again the rotation of a square and 2 arms that can be also deployed. Yeah, it can be modified carefully. Okay, maybe I didn't get to the right format immediately, but with a little bit of care, yes, I also packed this to a tiling. Okay, so 3 degrees of freedom, 5 degrees of freedom. So what this particular framework had something very interesting was that we were able to produce a parametrization of a trajectory in this high dimensional space, in the three-dimensional space. And in fact, we could parameterize it. So the question is that in general, it is not easy to find the direct parameterization of a auxetic one. So I want to show you the general methodology using expansive motions on this other example. So that's the goal, okay? So let me go back to the main slides. So we work in a four-dimensional, 4 degree of freedom, 4-dimensional space. Okay, yeah, so that's a summary. We saw the parameterization, the 3 arms, and the rotation between the 2 triangles. That's how we visualize the 4-dimensional space. Okay, so that's the tiling with the minimum area, and that's the deployment with the maximum area. Okay, so how do we do tiling to deployment trajectory design using all degrees of freedom? Would mean, well, you play around with each degree of freedom. So imagine that each degree of freedom is an actuator. Think in terms of robotics, think in mechanical terms. It's an actuator placed at those joints. And you have to coordinate the motion of 4. It's like driving a car where you have 4 parameters that you have to constantly keep under control. So it's a complicated problem if you don't want to produce collisions and self-intersections and other undesirable properties. So we'd like to do the design ahead of time and follow the trajectory and understand it in general. Okay. So this is an example, right, that I put here. So we can imagine we start in the tiling state and then we move. And I have no idea why my colors have disappeared. So somehow something mysterious happened to my slides, but it's okay. So as I said, we can apply what we did here. So here's what I wanted to point here. I start in the tiling state, and let's say I just applied this rotational. So I rotated the blue around the red one. So that's an interesting motion. You already see, because it didn't use the others. It looks more like a kagome lattice rather than this particular tiling. Then I start using the arms, and I can move them independently and move around until, you know, somehow it's random play until you get to where you want. So let's think, what are the properties of the deployed state? You can see that in the deployed state, all the faces are convex and they have maximal area. Yeah. So that's an interesting property. So because of this, the tiling to deployment problem is reminiscent of the Carpenter's ruler problem. So since this is a problem that was interesting about 20 years ago, and some of the young members of the audience may not have seen it, let me give you a brief overview, because the approach that I'm going to talk about, it's inspired by the solution to the Carpenter's ruler problem based on pseudo-triangulation, except that that one is in the finite case, and we are going to talk about something happening with periodic structures. Okay, so, but here's a more general question, right? So let's say that you have a periodic non-crossing framework, and the question would be, is it always possible to reconfigure it staying in the plane? And so you want to reconfiguring it without going in the 3rd dimension and without producing self-intersections along the way. Can you reconfigure it to a position where all faces are convex, or maybe max area, right? Like the example that we have seen. And in general, the answer to this question is no. So here's a very simple example. Even in the finite case, I can make this periodic, but it's obviously clear that if it's not working in the finite case, it will not work in periodic case. So you can deform this. This has a 1 degree of freedom. You can drag this, deform it, make one face convex, but this one, because of the chosen lengths of the bars, this one will always stay non-convex. So it is not possible to always deform to all faces convex, right? So our tiling to deployment problem actually is quite special. It's special in the sense that it has only one face that is non-convex, right? So you see, that's why I like this colored version, because you see that this star-shaped face actually is incident to itself in the infinite tiling. So the representative, the orbit of it. So it's only one face orbit, yeah, one representative. So this suggests a possible similarity to the Carpenter's ruler problem. So, also it suggests an approach to compute an expansive trajectory. So here's the question then. If we have only one non-convex polygon, can we convexify it? I'm not yet getting to the constraint that the face be maximum area, because even in the planar case, the Carpenter's rule solution based on pseudo-triangulation did not guarantee that you find the maximum area. So it's always something else is needed. But let's just assume that we want to convexify the face. So that is a question, an interesting question, okay? So let me remind you what the problem was. So the Carpenter's rule problem was the following. So I give you a polygon with, think of it like a robot arm. So the edges are rigid. Yeah, so the length of the edges are maintained throughout the motion. And we want to move it to reconfigure it from this position to a convex position without producing self-crossings along the way. Yeah, avoid self-intersections and not going to the third dimension. That's another thing. And now tiling to deployment, the counterpart of this problem would be, let's say that we have a bar and joint tiling, and let's assume that it has only one face. So that face is exactly a non-convex polygon. And we like to deploy it to a, let's say, first convex face, and then maybe, if we can, maximal area configuration. Yeah, so that's the formulation of the problem. Any questions? If anybody asks questions in the chat, just be aware that I cannot follow the chat in the setup that I have here. So if there is any question, I want to hear it. Feel free to interrupt me. Okay, so that's the problem. So let's move on. So let me give you a very brief overview of what the Polygon convexification algorithm was like. And I just realized this algorithm is 20 years old, and maybe it's time to find new problems where this approach can be used, and this is one example. So we want to convexify a planar non-crossing polygon, and here's what we can do. Yeah, so we want to go from here to a convex position. So we are going first to define a sequence of expansive motions. They will be induced by pointed pseudo-triangulation mechanisms that are expansive and with 1 degree of freedom. And this is, by the way, in the plane, not in the periodic case. We're going to extend this to the periodic case soon. But it is easier for me to do the explanations in the finite case, because as you will see, the pictures in the periodic case will become more crowded and it will be much harder to follow the ideas. So the ideas that I'm presenting are better explained in the finite case and will extrapolate in the periodic case. So what does it mean? So we start with the polygon, and we are going to put extra bars, fictive if you want. So and I'm going to restrict the distances between certain other pairs of vertices in such a way that I create a pseudo-triangulation. That's what you see here. It's a pseudo-triangulation. All the faces are pseudo-triangles. All the vertices have an angle larger than pi. But in the finite case, I also have to remove one edge from the convex hull in order to become a 1 degree of freedom. In the periodic case, I don't have to do that because they will automatically be 1 degree of freedom. So that's something very interesting when you move from the plane or sphere to the torus. Okay, and now this one is a 1 degree of freedom, so it starts moving. Yes, so you can deform it. And that's the trajectory, yeah? So when should we stop? We stop when the motion stops being expansive, and it stops being expansive because of the existing theorems, exactly when this mechanism stops being a pseudo-triangulation. And when does it stop? It stops exactly when some pair of edges, incident edges, align, so that if I go beyond this point, this angle will become smaller than pi, and this vertex will not be pointed. Yeah, so that's the idea. So so let me go back here. So we'll have expansive motions induced by pointed pseudo-triangulation, and we go as far as we can in the expansive direction. And when it's no longer possible, oops, then when an alignment happens, it's an event. So during the lifetime of the algorithm, so in other words, our trajectory is divided into shorter intervals. Each one of them is given by a pseudo-triangulation, and there is an event where they glue nicely to each other so that I can continue. So the trajectory will be made by these segments of expansive motions. So here at this event, the aligned edges are either frozen or there is a flip to obtain another pseudo-triangulation. So let me demonstrate this. So here I'm at an alignment event, and the two aligned edges, one is a polygonal edge, I cannot change it. The other is one that anyway I put there, and nobody prevents me from dropping it and putting another one, so that if I continue the motion, it will continue being a pseudo-triangulation. So what I did, I replaced this edge with this one. But you can imagine that this was happening when these were aligned. So it's at the event, some alignment happens, there will be degenerate situations that we had to handle. So when degeneracies arise, we make that motion. And as I will demonstrate a little later, you will see that in the periodic case, it will be quite hard to see exactly what is happening, because we are dealing with something extraordinarily symmetric in this particular tiling. But let me continue. Yeah, so now that we have a new pseudo-triangulation mechanism, we can continue, yes, and continue until the next event. And so after a small finite number of such steps, then here's, okay, so this one is going by itself. So some of these are frozen and aligned. And after a finite number of such small trajectories, you see this converges towards a convex position. So that is the convexification algorithm, okay? And you see that the final result is a convex polygon, but it's not maximal area. To be maximal area, it will have to be on co-circular. Okay, so now back to our tiling to deployment problem. So what do we want to do? Here are some questions. Yeah, so we like to go from here to a position where all the faces are convex and maximal area. Can we do it only with expansive motion? The answer would be no. Even the Carpenter's rule problem does not guarantee, and it's not possible actually. We can argue that in general, we cannot guarantee that we get to the maximum area. So we need to use non-expansive motions to get there. Can we do it only with auxetic motions? Can we do with the combination of expansive and auxetic? Is it the case that we can just use expansive motions and have this trajectory designed for as long as it is possible? And from that point on, when no expansive motion is possible, we switch to auxetic motions. And the answer to this is yes, in many cases, this is the situation. There are also cases where expansive is everything. Good, so let's do back to our example, our friend. So let's see what happens. Imagine this as being very tight, right? But I had to open it a little bit so that you see what the faces look like. So if this will be overlapping, if this would be the tightest conformation, this will be one on top of another, these bars, and we will not see these faces. But please try to imagine these star-shaped polygons as degenerate ones. And you are wondering, how can I pseudo-triangulate them? So if I deform it a little bit, you can see that this is now a non-degenerate polygon, and this is the one that has 14 possibilities of pseudo-triangulating the faces. Okay, homework, try it. But when it is very close, if you try, you'll see that one possibility is, in fact, to put a bar here between these two vertices, between the red and the green here. So when these are on top of another, this will be a degenerate triangle. And here I'll put an edge of length 0, yeah? And actually that's an interesting one. You'll see in a moment, yeah, what happens. But first, let me walk you over the 14 subdivisions. And the 14 subdivisions actually fall into 3 symmetry classes. Yeah, so we have, you can still identify here in this drawing the star-shaped version. And then we can put a bar here and then 2 small ones to form a category of subdivision. And this can be done in 3 possibilities by putting this or this edge. So these are equivalence classes. Or we can have this asymmetric with, again, the one in the middle and 2 asymmetric, not opposite like here, nearby, yeah? And then the final one would be just to put the small edges to pseudo-triangulate the large face. And this way we create smaller triangles here. So this is what we get. These are the possibilities for the expansive motion polytope. And the polytope itself exhibits the symmetries that are present in the combinatorics. So different classes correspond to different vertices here. Okay, so now what is a pseudo-triangulation guided motion? So let's look for it. So now I'm going to show you an example of what I did. And the nice thing is that I implemented, so to say, all this. I did it in Cinderella. Is the fastest way if you don't want to solve equations. It can be done, but the cost is quite high to try to solve these equations. So Cinderella, if it's done in Cinderella, is constructible with ruler and compass. And so all the frameworks that I'm going to show you, all the mechanisms, except one of them are constructible with ruler and compass. And when they are not, you have to do what a numerical solver would do. So, but I'm going to skip those details. So I have an animation for this in Cinderella, but let me walk you a little bit about give you a preview, yeah? So we have this tight configuration, but again, let me remind you, I would like to view it as epsilon deformed so that we can think about making it a pseudo-triangulation. And the pseudo-triangulation that I'm choosing will be the one that glues these adjacent vertices together. In other words, it is this pseudo-triangulation that I will be applying at that point. Yeah, so this is the one. And there are 2 of them, right? Because there are these 3 possibilities and there are also the other 3. So, so these will correspond to these extremal vertices of the polyhedron. So when I'm here, so I'm keeping fixed the arms and I will be moving only the rotational parameter. So this is equivalent to a degenerate pointed pseudo-triangulation with a degenerate triangle having an edge of length 0. Yeah, that's what we are doing. And here's how this moves. Yeah, so the vertex here is a degenerate triangle with the bar and the triangle adjacent to each other and glued together by a bar of length 0. And the motion is just a rotation, is parameterized actually just by the rotation of the triangles. And this, as you see, it looks like a different mechanism is the Kagome one. But it has to stop somewhere, and that's where it stops. It stops when these align. But because of the symmetry, so we are working not with a generic framework of this nature, but one with equilateral triangles. And in that case, when this aligns, everything aligns. Yeah, so it looks like this. And so now if you think about the algorithm, the pseudo-triangulation algorithm, the pseudo-triangulation algorithm says, okay, then I should drop this and maybe I should freeze what the edges that align, because then it will be a violation of the pseudo-triangulation property, right? If I don't do that. So if I do that, so let me do, and by the way, there are several ways of doing the flips, but I'm going to choose one so that I make it a little bit more challenging. So when I do that freezing, it will look something like this. You don't see much in this picture, so let me deform it a little bit so you see what's happening. So what I did, I was freezing So let's see, this is what aligned. Yeah, these were aligned. But remember that there was a little triangle here. This was glued together. So now I'm eliminating this bar because I'm making a flip at this point. But these, right? So these are still remaining aligned because this bar and that bar, because there was still an alignment. And so I am making this whole thing frozen. And the consequence of that is, so let's see if I can explain this better, is that with this thing aligned, I make here a big triangle. And I have now a configuration that has big triangles and small triangles. And now the faces are pseudo triangles. And by the way, let me say, there are many ways of doing it, right? At every such event, I have many options. I have just chosen this one to demonstrate as a possible pseudo triangulation. Yeah. So then I get another collection of triangles and I move it until it becomes again aligned. When it becomes aligned, what do? Again, I have to drop and flip some of the existing bars, the extra ones that I placed. And this is another possibility here. So I aligned all these into one big bar. And this mechanism that is visible here is actually, it's one that is not constructible with ruler and compass, but still I can animate it. And again, it deforms and deforms and deforms, oops, until something will align. And you guess by the motion that maybe these two will align. Yeah. So that's where I get an alignment. And because this is aligned, and this is aligned because of the symmetries, then the whole structure becomes a rigid body. And it happens that this rigid body aligns with another rigid body here, a triangle. So in fact, this whole thing is a tiling with triangles, and there is no way to move from here. It's actually rigid if I were to keep all of these big triangles and small triangles rigid and not deform it so that this is no longer aligned, because that would not be expansive. So this is a short trajectory. There are several others that are based on pseudo-triangulation. Remember that at every flip event, I have, at least in the first phase before I started freezing things, I had 14 possibilities. So there will be a number of them, but I've chosen this one because I got faster to the situation where I cannot continue. So I cannot continue just with the expansive motions. And look what happens. If I look at the original faces, they are not convex. Okay, so the framework is not yet convex. It's not yet at the maximum. But we can continue the deformation trajectory to the deploy configuration with auxetic motion. But expansive ones, at least from that particular position that I reached, are not possible. But there are other trajectories that may lead me to something a little beyond this step. Okay, I could not implement all of them, 14 times 12 or whatever will be at the next stage will be a lot of possibilities. And there will be at least 3 or 4 legs of this simulation because there are that many events. So let me, before ending, I want to show you at least the last leg of this animation. Okay, so I'm going to comment on the other in the background in a moment, but let me show you this one. So this is the one that started just from where I left it when I deformed with just a rotational motion. So the kagome in this extreme configuration, a line configuration. If this was just kagome, there wouldn't have an extra expansive motion. But since in fact, this has freedom here, I'm opening it up, keeping other pieces aligned. And you have to think about it as freezing this and this together, right? So it is, this whole thing is a bar. It's a rigid bar, so these are rigid triangles. And I cannot move beyond that because this angle becomes smaller than pi, and so therefore these vertices get closer to each other. This is not an expansive motion. but it might be auxetic. Yeah, we decided to move with expansive as far as we can, and only in the end, when there is no other option, then rely on auxetic ones, which even infinitesimally, they are a little more challenging to compute because we will be using not linear programming to find the infinitesimal motions, but other more complex calculations with quadratic situations. Okay, so this is the snapshot of one possible segment in the expansive trajectory. Okay, good. So now, just for fun, I brought here an example of one that we have shown in the past. This is for the structure with squares, not triangles. And this one is in fact obtained by a parametrization, and this moves very symmetrically due to that parametrization, and it moves very symmetrically all the way to the final deployed one. Yeah, so this one here, you also notice that it happens to move very symmetrically. So it maintains symmetries, although I have not enforced them. So they are not enforced. Ciprian talked about the fact that in this big 4-dimensional space of motions, we'd like to restrict our attention to those that preserve the threefold symmetry. And this was not enforced, but it came naturally because of the choice of the proper pseudo-triangulation to do it. I could have chosen others that would have broken the threefold symmetry. Yeah, whereas this one was completely parameterized with a mysterious parametrization that had to be computed separately. It's just through geometric insights, not through a general technique as we do it here. So this is through this expansive motion based on pseudo-triangulation technique. Okay. Any questions? Okay. So let's see. So I'm getting close to the end of my talk, actually. I think I told you most of the things that I wanted to tell you. So let's see. So the idea is that we did use expansive motions in this fashion inspired by the Carpenter's rule problem algorithm based on pseudo-triangulations, based on the properties of periodic pseudo-triangulations. And here is the message, the take-home are the take-home messages, right? So there are two messages here, that using purely expansive motions, you may not necessarily reach the highest area, the most deployed version. And the reason for this being that even for a single face, if you want the most largest area, you want a very special shape of the convex face. And that convex face that pseudo-triangulations can lead you to may have alignments, and that would not be the maximum area. So after you can no longer use expansive motions, you may still look for auxetic motions. They still exist. In this case, the auxetic behavior will be present even after the expansive part of the trajectory has been completed, okay? And I can argue that even in the finite case, in the Carpenter's rule problem, the expansive motions algorithm based on pseudo-triangulation would not take you to the maximum area. You'll have to have this infinitesimal detail at each step in order to guide you towards that maximal area. And that's it. So I guess I'm at the end of my talk and I'm ready for questions. And with your permission, I'm putting here a list of publications in which the preliminaries for this talk have been laid down. And starting about 10 years ago. And the rest is in Ciprian's talk also, some of the other details.